Let's start with an overview on fuel cells, what they are and how they work. After this module, you will be able to describe the working principle of a fuel cell, to list and define the main electrochemical equations that describe how a fuel cell works, calculate the fuel cell voltage in various conditions, and to evaluate the possible benefits and application of fuel cell systems. But what is a fuel cell? A fuel cell is a device that converts chemical energy from the fuel into electrical energy through electrochemical reactions. The most common reaction is the one between hydrogen and oxygen to form water. In this reaction, hydrogen and oxygen react spontaneously and there is an exchange of electrons. If we put hydrogen and oxygen together in a tank, we get spontaneously water. But it doesn't generate electricity. So how can we use this reaction into a fuel cell to generate electricity? The key point is that hydrogen and oxygen in a fuel cell are separated into two different electrodes, divided by a membrane called electrolyte. The electrons exchanged in this reaction cannot pass through the electrolyte, but they are forced through an external circuit. So we have electrons moving into an external circuit, which means we have a current generated. The principle is very similar to the one of batteries, but the difference is that in batteries, the reactants and the products are stored in the electrodes. So when we use the battery, we discharge it, and then we have to charge it again. So they usually work in cycles. But fuel cells don't, because fuel and oxygen, they flow continuously through the cell. So as long as they flow through the cell, we can generate continuous power. We're very interested in fuel cells because they are very efficient. And to explain why, we can compare to a traditional thermal process. If we want to generate electricity from a thermal process, we have to go through many different steps. First, the fuel can be burned in a combustion chamber to turn chemical energy into thermal energy. And we already have some losses into this process. After the combustion, we generate hot gases, and this can be used to spin a turbine, for example, or to move an internal combustion engine. So we can convert the thermal energy of the hot gases into mechanical energy. And we have a big amount of thermal loss and some friction loss in this process. Finally, moving parts, rotating parts can be coupled to a generator to turn mechanical energy into electrical energy. And again, we have some friction losses and maybe also some thermal losses in this process. So at the end of the day, we can recover basically 30–40% of the energy contained in the fuel and the rest is lost. But in an electrochemical process, such as the one occurring in the fuel cell, we convert the chemical energy directly into electrical energy. So there's just one source of loss instead of three, which reduces the total losses considerably. And by the end of the process, we have recovered about 50 or 60% of the energy contained in the fuel. There are four components mainly that constitute a fuel cell and ensure the correct operation. Two components are the two electrodes. Anode is the electrode where the fuel goes through, and cathode is the electrode where the air or the oxygen flows through. The electrodes are separated by a membrane called electrolyte. And the fourth component is the external circuit through which we want the electrons to flow. Characteristic of the electrolyte is that it's not conductive to electrons. That's why they are forced to pass through an external circuit, and that's how we can actually use the current. The electrolyte can be made of different materials depending on the type of fuel cell, but each material is conductive only to one particular ion. So what happens inside the fuel cell is that the hydrogen loses an electron. The electron goes from the external circuit while the proton reaches the electrolyte. On the other side, the oxygen receives an electron, becoming O2 minus, a negative ion. This positive hydrogen ion and negative oxygen ion, they meet. One of them can pass through the electrolyte, so that it can meet the other ion. They can react and form water. So water is formed either on the anode side or the cathode side, but electrons are passing through the external circuit. The most common fuel cell type is called proton exchange membrane fuel cell, because the electrolyte is conducted through a proton, so a nitrogen ion, as explained before. We will see more in details in next modules the different types of fuel cells, but one quick example, we have also molten carbonate fuel cells. In this case, the electrolyte is conductive to carbonate ions, and slightly different reactions occur inside. Another example is solid oxide fuel cell. In this case, the electrolyte is conductive to oxygen ions. We can zoom in into the electrolyte structure and take a look more in detail. The electrolyte is a porous material, so that the fuel, the gases, they can diffuse inside the pores, as is depicted in this figure. But the material itself, which is here represented with these green balls, can let only an ion pass through the solid material. In this case, the oxygen ion, O2 minus. So where the fuel diffuses through the pores, it can get in contact with the oxygen ions that are instead passing through the solid material. And everywhere in the electrolyte material, there are also these red balls, which represent another element, the catalyst. The catalyst is an element that doesn't take part in the reaction, but it accelerates it. So the surface where catalyst, electrolyte material, and the pore, they are all three in contact, is where the reaction can take place, because the fuel can meet the oxygen ion in the presence of the catalyst. Let's take a look now more in detail to the fuel cell electrochemistry, so that we can quantify how much voltage and how much energy is produced in the fuel cell. If we consider this simple reaction, hydrogen and oxygen to form water, we can describe the energy released by this reaction through the Gibbs free energy. So the variation of Gibbs free energy for the reaction is Gibbs free energy of the products minus Gibbs free energy of the reactants. Before we go forward, we have to make some assumptions and clarify these assumptions. The first one is that we consider ideal gas, so we will always consider ideal gas low. And this is quite a reasonable assumption when we talk about gases like hydrogen or oxygen. It can be not valid if the presence of water vapor is very high. So in some condition in which, because water vapor is produced in the fuel cell, is generated in the fuel cell, there are some conditions in which the concentration of water vapor is too high and this assumption is not valid anymore. The other assumption that we are making is that there is no oxidation of other species, but just hydrogen. The most important equation that we can define is the one describing the ideal cell voltage, also called Nernst voltage or Nernst potential. The ideal voltage in standard conditions, so atmospheric pressure and 15 degrees Celsius, it is the ratio between the variation of Gibbs free energy for the water reaction and a factor that is the multiplication between the Faraday constant and the number of electrons exchanged in the reactions, which in this case is 2. There is also another term that is a function of the temperature and the pressure. So if we are not in standard condition, we have a term that varies, being Nernst potential, compared to this first term. And this term can be understood if we go to refresh a little bit the chemistry notions. The Gibbs free energy variation for a reaction at a given temperature and pressure is a function of enthalpy and entropy. So we can define it for a constant temperature as the Gibbs free energy variation at standard condition minus a term that is a function of temperature and reaction entropy generation. And the entropy of the reaction is described by this formula in this slide. It's a function of the concentration of products and reactants. Now, because we have made the assumption of ideal gas, this constant is actually the gas constant, R. And the concentration can be replaced by the partial pressures of the products and reactants, which simplifies this formula. And we get to the final formula that is here, which we see this term with the temperature and pressure. So we can see from here that if we increase the temperature of the reaction, this term that is subtracted is bigger. So we subtract the bigger terms, it means that the final ideal voltage is lower. On the other hand, if the pressure of the oxygen is higher, this term with the logarithm is smaller. So we subtract a smaller term, which means that the Nernst potential is higher. The actual voltage, of course, is lower than the ideal voltage because there are several sources of loss that make the voltage lower. And this can be classified mainly in three types. First, we have activation loss, which is related to the energy that is needed to activate the reaction. And it can be described with this empirical formulation. We have also ohmic loss, which is related to the current flowing through the external circuit. And this follows the ohmic law. And then we have diffusion loss, which is related to the energy that is lost in the process of the gas diffusion in the fuel cell and through the electrolyte. So the gases have to diffuse to reach the area where they can react. And in this diffusion, of course, they have to move, they encounter friction and so on. So there is a loss of energy. And this can also be modeled through an empirical formula. So this is a graphic representation of the losses that we have. Activation losses related to activation of the reaction, diffusion losses related to diffusion of the gases, and ohmic losses related to the current through the external circuit. So the actual voltage is the difference between the ideal Nernst potential and the losses. And if we depict the voltage as a function of the current, we can get this curve, this characteristic curve, which is qualitatively is the same, it looks the same for all types of fuel cell. We can see there are three different regions in this curve. A first region for very low current is represented by a very sharp decrease in voltage respect to the ideal voltage. And here's where the activation loss is dominant, because for low current, a lot of energy is needed to activate the reactions. Then there is a large region where the voltage is decreasing linearly with the current. And this is where the ohmic potential, the ohmic loss is dominant, because the ohmic loss is linearly related with current. And finally, a third region where we see again a quite sharp decrease in voltage, and is where the diffusion loss is dominant, because for very high current, it means that the reactions have to occur very fast. So the gas also have to diffuse very fast. So they lose more energy in this. Eventually, there is a limit for the current, a maximum value of current above which the gases simply cannot diffuse as fast as it's required for the reaction. So the voltage drops to zero. To define the performance of the fuel cell, we can define two variables. One is the fuel utilization, and this is the ratio between the fuel that is consumed in the fuel cell and the fuel that is fed to the fuel cell. So it's an indication of how much fuel is reacted, so how efficient the fuel cell is. It is proportional to the ratio between current and fuel flow, and the proportional constant for pure hydrogen is the ratio between molar mass of hydrogen and Faraday constant. The fuel utilization can never be 100%. This is an unreasonable expectation. That's mainly because at the end of the cell, where a lot of fuel has reacted, so the concentration of the fuel is low, the diffusion losses are too high. So the fuel cannot diffuse enough, cannot react. So there's always around 20 or 30% of fuel that is not utilized. The unutilized fuel is usually then all collected in a off-gas burner or in a post-combustor downstream the fuel cell, so that the energy still contained in the unutilized fuel can be recovered through combustion and generating heat. Another variable that determines fuel cell performance is the thermodynamic efficiency. And this can be defined as the efficiency for any thermodynamic process. So as the ratio between the useful product, which is electrical power, and the inlet power, which is the one contained in the fuel. So fuel flow times the low heating value. We will see more in details in the next module, what are the applications of different types of fuel cells. But just to give a quick overview, fuel cells, as a state of the art, they can generate power in the order of a fraction of a watt or up to a few hundred or 1,000 kilowatt. So they are very good to use for both transportation and for stationary applications like energy generation for buildings, for hospitals, for microgrids, and so on. And because the electrochemical reactions are exothermic, so they release heat, the fuel cell can provide not only electricity, but also a certain amount of heat. So if heat can be considered a useful product, they can be used for cogeneration of electricity and heat, for example, to heat the building or to produce domestic hot water. So the total efficiency of the process, of course, would be much higher. Nowadays, the current barriers that limit the fuel cell use, I can mention a few. First of all, is the high cost of the materials, especially the catalyst can be quite expensive, and the weight is quite high compared to other engines. So this limits, for example, the exploitation in transportation. And also the lifetime is quite short. If we compare to internal combustion engines or gas turbines or other technology for energy conversion, fuel cells have a lifetime that is much, much shorter. Like batteries or even more than batteries, they degrade quickly during their life, which combined with the high cost makes this investment still not very attractive for a lot of applications. In conclusion, fuel cells are very efficient systems for energy conversion. This is thanks to the direct conversion of chemical energy of the fuel into electricity. So it's a very promising technology. The ideal voltage is calculated from Gibbs free energy, and then we can subtract the losses. There are mainly activation, diffusion, and ohmic losses. And we can then calculate the final performance of the fuel cell. Main barriers to commercialization are the high cost and short lifetime, but nevertheless, applications for microgrids and for transportation are very promising. See you in the